Okay, this is the third video in the redox series, and I'm going to introduce a concept here. It's an artificial concept, but it's an important one. It's covered in every book that talks about redox, and that is the concept called oxidation number. Okay, so oxidation number, again, it's an artificial concept, but essentially what it is a measure of is that if you're looking at every atom in a compound or a polyatomic ion, looking at every atom, the oxidation number essentially says how many electrons, or makes a statement about how many electrons that atom still has, assuming that it has electrons according to some rules. Okay. Now the rules are covered in your book. It's in table 4.3, and I'm going to kind of cover what the oxidation rules are. First of all, in any element, meaning either a monatomic or diatomic element, such as chlorine gas, or such as nitrogen gas, or such as elemental zinc. Okay, the oxidation number for all of these elements and/or compound elements is 0. So if it's it's an uncharged, not an ion, the oxidation number in each of these is 0. Okay. Now, then it goes on to say some other rules. So you can always take, for anything that is uncharged, it's 0. But for anything that's charged, there'll be an oxidation number associated with it. So basically, the rules are oxygen always has oxidation number of -2. Except in some extreme cases. Oxygen always has an oxidation number of +1. Okay? And then goes on to say elements in the sodium column, basically the lithium, sodium, potassium column, the 1A column. So that's basically the 1A metals. For example, sodium. They're always +1. The 2A metals, for example, calcium, are always +2. Okay, and then it goes on to cover some other rules, and I won't draw those right now. But a lot of them have to do with the halogens, what chlorine is like. Because again, chlorine is one of these that's a little shifty. And in fact, I'll kind of cover this and show you why it's shifty. So anyway, using these rules, we can take something like hydroxide and say, okay, in hydroxide, the O is a -2 and the H is a +1. If you add those together, that explains the negative charge. So sure enough, the oxidation state of oxygen is -2 and H is +1. Okay. Let's take something not so obvious though. Let's take hypochlorite. Okay, it's a polyatomic anion that looks like this, has a single negative charge. What is the oxidation number of chlorine in hypochlorite? Well, again, we know that oxygen is -2 because that's what the rule says. The rule says unless oxygen is as a gas, like oxygen gas, it's -2, right? The whole polyatomic anion ends up -1. That means that chlorine in this state has to be oxidation number +1. Okay, which essentially means that chlorine has 1 fewer electrons than it has as an atom. So again, it usually has 7 electrons available to react in that second in its row, but since it's in a +1 state, it actually only has 6 when it exists as hypochlorite. Okay. You can kind of look at this too. I think it's worth maybe looking at a picture of this. Is that here's oxygen with its 1, 2, 3, 4, 5, 6 oxygens, and since it's -2, it's grabbed 2 of them from chlorine. Chlorine usually has 7, but it's grabbed 2 of those, and the chlorine atom is attached to the O like this, and chlorine will have 1, 2, 3, 4, 5, 6 Again, it usually has 7, but has 6. That's why it's +1. And when you take these together now, that's hypochlorite. So again, oxygen tends to be kind of a hog, and these electrons are sort of shifted towards oxygen, but they're semi-shared with chlorine here, which brings 6 of its 7 electrons to the table. So chlorine in this case is short an electron, which is why it's in the +1 state. Okay. We can go on and draw other chlorine-oxygen polyatomic ions like chlorate or perchlorate and all that. And you'll show in what we see in all those is that chlorine actually has a different oxidation number in that setting. It's probably worth actually drawing that. Let me draw, I guess, the most extreme one, which would be perchlorate. That's ClO4 minus. Okay, and that's known as perchlorate. By the way, this is a very highly oxidizing agent. Hypochlorite, which is what I showed just previously, ClO, is a mild oxidizing agent. It's bleach. We actually use it to oxidize things in the household because it tends to actually kill bacteria and forms other kind of softer oxidizing activities. Perchlorate is a very strong oxidizing agent. And basically it's because the chlorine in this polyatomic ion, instead of previously it was +1, and this it's actually +7, and you'll see why in a second. Actually, you probably see why quickly, is that each oxygen is at -2. You got 4 of them. That's basically -8 from the oxygen standpoint. But the whole ion's only -1, which means that chlorine has to be +7. Again, each oxygen is -2. So chlorine in a perchlorate polyatomic anion is actually in the +7 oxidation state. Okay, which kind of means chlorine is given up all of its outer shell electrons, all 7 of them. And if you think back, remember chlorine is one that actually usually likes to pick up an extra electron to get to 8. But in this case, in perchlorate, it's given up all 7 to oxygen. You can kind of draw it out. It looks like this. And again, each of these lines I'm drawing are pairs of electrons. So in this case, 1, 2, 3, 4, 5, 6, 7 pairs of electrons are surrounding chlorine, but those electrons have gravitated much closer to the oxygen. Oxygen tends to grab electrons more so than chlorine in this case. So anyway, this is what perchlorate looks like as a net negative, because this oxygen's a negative. The other 3 are stable, so that's why that one's negative. But and we even touched on this when we talked about naming early on. Okay, I think I'm going to end this one and pick back up on other uses of oxidation number, especially oxidation number, using oxidation number in practice to balance equations.